All right, we're moving on to section 2.2 now. And this is moving on from getting the derivative at a point on a graph and defining the derivative function. It's the entire function. What is the derivative for an entire function? It's amazing that the system works. It really does. But what I want to get to is go ahead and get over to the slideshow and talk through some things and let you see what we're talking about. So I'm going to do that now. All right, and now I'm going to make it into a slideshow. All right, so one of the things we're going to define the derivative function and we're going to graph it and identify where a function has no derivative. That's another key point to understand, that things that can't happen and no, it's not differentiable at a specific place, and we'll talk about that. So one of the things I want to start with is what we've been talking about so far has been finding the derivative, finding the rate of change at a point, finding the slope of the tangent line at a specific value of c. And what we've done is typically right up here. You know, this notation is saying the slope at c is equal to the limit as x goes to c. So this is approaching c is what the idea is. And then you've got this, the change in y over the change in x. What they've done now is they've converted this to bring in, this is where the h comes in that we were talking about in the previous functions. And it has to do with the fact that instead of going from x and have that x get closer to c, what they've done is they've added a small h, added h to c, and let that h go to 0. So it's approaching c in that fashion, okay? And this works numerically, it works more efficiently, and in general, so the idea of the definition of now this rate of change, the slope of the tangent line at a particular, point, or it's at any point now, is the limit as h goes to 0 of this situation where we added h to c. And that's where we can see the formula. You have f of x plus h, minus f of x. And we'll show that in just a second again. But as h goes to 0, you end up the c's canceling, you end up with just h in the bottom. And you end up with this function as h goes to 0, instead of as x going to c, now h is going to 0. And that's what we use from now on, okay? So the definition now of derivative function f prime, that f prime now has meaning as the derivative function. F prime of a function is the limit as h goes to 0 of f of x plus h minus f of x over h, provided the limit exists. If f has a derivative, then f is said to be differentiable. Okay? Here is now the definition we're going to be using for, and then I've made reference to it as the limit definition of derivative. It's the limit defined, okay? Limit definition of derivative. Okay, so here's an example. I'll tell you what, this has got a radical. We're going to do that on another day. What I'd like to do right now, and this is another problem that's got to do with surface area. We'll hit that on another day also. But situations where a function doesn't have a derivative. Notice what that's saying here. Look what's happening. It needs to be a smooth curve. It can't have a corner, okay? So the way they've got it said here, what's happening there, if it's got a corner, notice the word corner is used here. That means as you come in from the right, the slope is one value. And if you come in from the left, the slope is a different value. So if that's the case, it's going to end up being some sort of a corner. It's not a smooth curve. It's got to be exactly the same. The slope coming in from the right has to match the slope coming in from the left. And if it doesn't, it's not differentiable at that point. It has a corner, okay? And the next page on that, let me see, did I lose a page? Yeah, no, that's it. And it happens at FC. Okay, so that's what it looks like. So if the slope is one value on this side, it's another value coming in here. Therefore, it's not considered differentiable at that point. X, that doesn't fly. Also, the last one is if you've got a point, if they come to a cusp, it's called. If you've got what is called a cusp, This situation is, that's evidence that that does not have a derivative at that point. Both one-sided limits are infinite. This is going up, getting taller and taller and taller. It's going to infinity. This one is also going, if you're coming in from the right, it's going up to infinity. They're both infinite. One equals negative infinity, the other equals positive infinity. You know, the slope is getting higher and higher and higher and higher. Well, this is negative. You know, the slope is getting negative, 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 but they're both going to an infinite kind of a situation. It turns out that is a cusp, and that is not differentiable as well. So if it's anything but a smooth curve, it doesn't fly, okay? No sharp corner. Well, even this is an example of another cusp. You know, if your graph looks like that, it does not have a derivative. Okay, so these are the three situations that they point out here. If you've got a jump discontinuity like this, that's obvious. You know, H is discontinuous at 0. H prime does not exist. H prime at 0 does not exist there. This says it's continuous, okay? This is continuous, but the slope coming from the right and coming from the left are different. And therefore, this is not differentiable either. And this one over on this side, F is continuous at 1 and F prime at 1 exists. So it turns out, it does turn out, you can see this is a parabola and this looks like it's going to a straight line, but it has to be that the slope of this line has to match the slope of this curve at that point. All right? So that's section 2.2, and look at it, take a look at the problems, and keep smiling.